Good day everyone. I am Dr. S. Selvalakshmi, Assistant Professor of Physics, the Standard 5 Works Rajaratnam College for Women, Sivakasi. Welcome to the presentation on storage of hydrogen, unlocking the future of clean energy. Today we look at why hydrogen is more important for clean energy and the ways to store hydrogen in a more efficient way. Let's start by asking, why does hydrogen storage matter? Hydrogen is a clean energy carrier. When we use it, it only produces water vapor. This makes it perfect for reducing pollution in big industries and transport. However, we have faced a fundamental storage challenge. Hydrogen has an extremely low density under normal conditions, making it impractical to use like petrol or diesel. Think of it this way. Storing enough hydrogen to power a car would require a massive balloon at atmospheric pressure. Hence, we need to find smart ways to store it in a smaller volume. Solving the storage problem is what makes everything possible, from hydrogen cars to clean electricity for our homes. Let's look at the science behind the problem. First challenge is the density dilemma. At normal temperature and pressure, hydrogen is very light. At room temperature and pressure, hydrogen's density is mere 0.09 kilograms per cubic meter. Its energy per liter is about 10 times less than petrol. Second challenge is the safety issue. Hydrogen is the smallest molecule. It can leak easily through tiny holes. It can also catch fire easily. This means we need very safe tanks and systems to handle it. Now, the first solution is compressed gas storage. This is the most common method today, especially for cars. We squeeze hydrogen gas to very high pressure, about 700 times normal air pressure, and store it in strong, lightweight tanks made of carbon fiber. This works, but it uses a lot of energy to compress the gas, and the tanks are still expensive. Another method is liquid hydrogen storage. Here we cool hydrogen to minus 253 degrees Celsius until it becomes a liquid. This makes it much more compact. This is great for rockets and ships, but cooling hydrogen to such low temperature uses a lot of energy that comes at a steep energy penalty, about 30% of hydrogen's own energy. Also, special insulated tanks are needed to keep it cold. The infrastructure for handling and transporting this cryogenic fluid is also specialized and costly. So, while the density is right, the efficiency and economics are challenging. Looking beyond simple physics, we enter the frontier of material science. This slide shows three promising avenues for materials-based storage. Instead of using high pressure or extreme cold, we use special materials to trap hydrogen. First, metal hydrides. Certain metals and alloys can absorb hydrogen atoms into their crystal structure like a sponge, forming a solid compound. This happens at much lower pressures than compressed gas, offering a safer profile. Second, chemical hydrides. These are compounds that undergo a chemical reaction to release hydrogen. They can offer very high storage capacity, but often require complex processing to regenerate. Third, carbon materials like graphene and nanotubes. The promise here is revolutionary, storing hydrogen at near ambient pressures in a compact solid form. The current research race is focused on improving the speed of charging and discharging, the number of cycles these materials can endure, and of course, bringing down their cost. Focusing on carbon materials like graphene and carbon nanotubes, these materials have a huge surface area. Imagine a football field squeezed into 1 gram. This large area helps to trap hydrogen molecules. They are lightweight, made from common carbon and could be low cost. The challenge is to make them store enough hydrogen at normal room temperature, not just in very cold labs. For grid scale energy storage, we can think much bigger, underground. This isn't science fiction. We already do it with natural gas. Suitable geological formations like salt caverns can safely store thousands of tons of hydrogen. Hydrogen produced from excess solar power in the summer could be stored underground and used to generate electricity or heat in the winter, providing seasonal buffering. It is a great large-scale solution, but it only works in places with the right kind of geology. So, what's next? Our innovation roadmap is guided by 3 interconnected challenges. First, reduce cost. Second, improve performance, which is faster refueling and longer lasting materials. And the third is the create hybrid systems. Combine methods like a pressure tank with a metal sponge for better safety and capacity. Research in new materials and better tank designs will help us reach these goals. To conclude, hydrogen storage is the key to a clean energy future. Technology advancement in this field is not optional, it is absolutely critical. There will be no one-size-fits-all solution. Instead, we will see a portfolio of application-tailored solutions, compressed gas for passenger cars, liquid hydrogen for ships, underground storage for the grid, each playing to its strengths. Realizing this future requires sustained investment and innovation from both the public and private sectors to drive down costs and scale up technologies. If we succeed, we will enable hydrogen to fulfill its promise, powering our transport, industries and homes sustainably for generations to come. The journey begins with the storing of this hydrogen molecule. Thank you. Let's meet in the next video. Goodbye.